Time has texture, a quiet pull that can loosen a minute or make it dense. Not with gears, not with a hidden metronome, but with motion chosen carefully and gravity's soft hand on the loom of space. Imagine a civilization that measures life by tempo rather than distance, that learns to sail the universe by listening for where time runs thin and where it gathers weight. Close your eyes and picture first light. Along the coast and high on the ridges, a lattice of clocks wakes and compares notes. Far above, a ring of silent sentinels circles the earth, each one keeping watch on the beat. Nothing shouts, nothing flashes. Yet when a clock climbs to thin air, it slips ahead, and when another lingers near heavy ground, it falls slightly behind. No banners, no thunder, only the hush of seconds changing shape until a pattern appears. The world looks unchanged. Your coffee cools the same. Still, the whole map of moments is drifting. Tonight we will walk slowly through this idea. We will touch the physics that lets speed stretch seconds and mass make them heavy. We will look at light used as a clock, at twins who trade birthdays with a journey, at instruments that fly and return with time in their pockets. We will learn how space-time holds a mirror to motion, and why your days are already woven into that fabric. Let the room grow still. Let curiosity soften into wonder. If these crossings bring you ease, a quiet like or a simple subscription helps this small harbour reach others who are awake and looking for calm. Tell me the hour on your clock in the comments and I will chart our midnight fleet so future voyages arrive as your night begins. When you are ready, we set out together into the strange, beautiful weather of time. Before physics, before astronomy, before language, there was rhythm. The first humans may not have had words for time, but they knew its touch. They felt it in the cycles of the sun and moon, in the ebb and flow of tides, in the pulse of their own hearts. Something was moving always, something flowing, invisible but constant. That something we would come to call time. At first it was measured crudely. The rising of stars, the blooming of flowers, the wear of bone and breath. Ancient societies marked the seasons by carving lines into stone, aligning monuments with the solstices. Time was celestial, a dance of lights across the sky. The heavens became a clock, and with it, civilization began to count. But as our world grew more complex, so did our need for precision. Enter the clock. The earliest clocks were sundials, instruments of shadow and light. Later came the hourglass, the water clock, and the mechanical escapement, each more accurate than the last. These devices divided the day into hours, the hours into minutes, the minutes into seconds. Eventually, we built clocks that counted not the swing of pendulums, but the oscillations of atoms. Modern atomic clocks measure time with astonishing precision, losing less than a second over millions of years. But here's the mystery. No matter how fine the gears or stable the atom, these devices do not tell us what time is. They only give us a way to measure it. We still don't know what time is. We know what it does. It flows. It allows cause to precede effect. It separates past from future. But what is it made of? Is it a fundamental ingredient of reality, or an emergent phenomenon born from change? This question lies at the heart of modern physics, and to explore it, we must go beyond clocks, beyond calendars, beyond even language itself. We must ask not just how time passes, but how it bends, because time is not rigid, it has shape. In the Newtonian world, the physics of falling apples and planetary orbits, time was absolute. It ticked uniformly throughout the cosmos, unaffected by motion, gravity, or perspective. It was the great metronome behind the curtain, invisible but ever present, setting the rhythm for everything that happened. But something didn't quite fit. By the late 19th century, light had become a problem. The famous Michelson-Morley experiment, conducted in 1887, attempted to detect the motion of Earth through the so-called luminiferous ether, a hypothetical medium through which light was thought to travel. But the experiment failed. No matter how they oriented their instruments, The speed of light appeared constant. This constancy was baffling. In a world where speeds added and subtracted, where a ball thrown from a moving train travelled faster than one thrown at rest, light refused to follow the rules. Enter Einstein. In 1905, he proposed something radical. What if the speed of light is not just a feature of light, but a fundamental limit written into the structure of the universe? What if, no matter how fast you move, light always passes you at the same speed? To preserve this rule, something else had to give. That something was time. In Einstein's theory of special relativity, time and space are not separate entities. They're woven together into a four-dimensional continuum, space-time. In this view, time is not an external backdrop, but a dimension like length, width, or height. Events do not simply happen in time. They happen in space-time, where the distance between events is affected by both their separation in space and in time. The geometry of space-time is described not by the Pythagorean formula used in Euclidean geometry, but by a slightly altered equation that accounts for the behavior of light. In this new geometry, the space-time interval between two events, something like the true distance in space-time, is calculated using both spatial and temporal components, but with time contributing a negative term. This mathematical shift carries a physical consequence. Observers in different frames of motion will disagree on the amount of time between two events. Time is no longer universal. It is relative. If you move through space, your journey through time is altered. The faster you go, the more your time stretches. The slower you move, the more time you experience. There is a trade-off, a cosmic balancing act, between motion through space and motion through time. Time, it turns out, is not a constant march forward. It is a curve, and its shape changes depending on how you move through the world. Let's step away from theory and into your own body. Right now, as you listen, your cells are aging. Chemical reactions are taking place in your bloodstream. Electrical signals are flashing through your nervous system. From your perspective, everything feels normal. Your sense of time is smooth, continuous. A second feels like a second. But that smoothness is local. Zoom out far enough, and you'll find that your personal sense of time is just one slice of a much larger tapestry. Time moves differently in other places. For someone flying overhead in a fast-moving jet, time ticks a little slower. For someone standing on a mountain peak, farther from Earth's centre of gravity, time ticks a little faster. The differences are minute, but measurable. The shape of your time is not universal. It is yours. You are carrying your own rhythm through space-time. And it's not just humans. Every object, every particle, every clock carries its own sense of now, shaped by its motion and position in gravitational fields. This realization transforms time from a single river into a network of branching streams. Each observer travels their own path, and the ticking of their clocks, their biology, their technology, their thoughts, reflects that path. When they reunite, they may find that their streams have diverged. The universe does not grant a single now to all beings. Instead, it grants each traveller a unique timeline, one defined not only by when, but by how and where they move. This is what physicists call proper time, the time experienced along a particular world line through space-time. It is your personal clock and no one else's. It is the time written into your heartbeat, your breath, your thoughts. So when we speak of time dilation, we are not talking about distortion in perception. We are talking about real differences in the unfolding of events, real differences in aging, in duration, in memory. Two people can leave the same point, take different paths, and return changed. Not just in space, but in time itself. And this is the great turning point in our story. Time is not just a parameter we live inside, it is a path we walk. And the shape of that path depends on how we move. In the chapters to come, we will follow those paths, to the edges of stars, through the corridors of motion, into the silence of black holes, and to the still places where time ceases altogether. But for now, just consider this. You are not in time. You are time, and you are moving through the universe as a shape. Long before the world knew his name, before he stood on the stage of history or saw his equations scribbled on chalkboards across the globe, Albert Einstein sat quietly at a desk in a patent office in Bern, Switzerland. It was 1905, a year now remembered as his Annus Mirabilis, or miraculous year. But to Einstein, it was a year of quiet thought. He was 26 years old. His job was to examine patent applications for mechanical devices. But while the world passed inventions across his desk, Einstein's mind wandered elsewhere, into the hidden workings of the universe. His imagination was always awake, always alive. While the clocks ticked and the city bustled beyond the window, Einstein was not thinking of gears or machines. He was imagining himself riding alongside a beam of light. What would that look like? What would that feel like? Would the light appear frozen beside him? Would the world around him vanish into stillness? No one had ever asked questions like these before, not in this way, but Einstein sensed that the answers might unlock something fundamental, something that had been misunderstood for centuries. Until then, most people believed that time and space were absolute, that if two events happened at the same moment in one place, they would happen at the same moment in all places, that everyone in the universe, no matter where they were or how fast they moved, would agree on the order of things. But Einstein began to suspect something radical. What if that wasn't true? What if time was not fixed, but flexible? What if space could bend and twist, depending on how you moved? These were not just dreams. Einstein began to build the framework for a new reality, a theory that would come to be known as special relativity. And in doing so, he reshaped the very foundations of physics. At the centre of his vision was a single, unwavering idea. The speed of light is always the same, for everyone, in all frames of motion. This was not an assumption. It was a principle, a rule that could not be broken, and from it, strange consequences would unfold. But strange or not, they were real. To understand why Einstein's idea was so revolutionary, imagine two people. One stands still on the ground, the other rides past in a speeding train. A bolt of lightning strikes a nearby tree. To the person on the ground, it happens in an instant. But to the person on the train moving rapidly forward, the flash seems to come a moment later. They disagree on when it happened. In classical physics, such disagreements were awkward but resolvable. You simply adjusted for their positions or speeds, assuming there was some underlying true time. One real clock to compare against. But Einstein discarded that assumption. He declared that there is no universal time. Each observer has their own clock, and all clocks are equally valid, so long as they are measured in their own frame of reference. This led to an even deeper revelation. If the speed of light is constant, then time and space must adjust themselves to protect that constancy. In other words, the faster you move through space, the slower time must pass for you. And the more you resist time's flow, the more you accelerate through space. This trade-off is built into the fabric of the universe. Einstein expressed this relationship through a now famous equation that binds energy, mass, and the speed of light together. Energy equals mass multiplied by the speed of light squared. But tonight, let us say it like this. Energy is equal to mass times the square of the speed of light. It's a simple phrase with profound meaning. It tells us that mass is not a separate thing from energy. They are two forms of the same essence, and light, unchanging, ever fast, is the bridge between them. But even more than this, special relativity gave us something else: time dilation. Einstein's theory predicted that for someone moving close to the speed of light, time would pass more slowly compared to someone at rest. This wasn't just a poetic metaphor, it was a testable consequence, and years later it would be confirmed. Atomic clocks flown aboard airplanes ticked more slowly than those on the ground. Particles moving at near light speed in accelerators lived longer than they should have. Even today, GPS satellites must adjust for the difference in time caused by both their speed and their position above Earth's surface. It is not science fiction, it is science. And yet it all began with a man in a modest office, dreaming of light. Einstein's insight was not merely mathematical, it was philosophical. It told us something humbling about our place in the cosmos. There is no privileged observer, no single point from which to declare what is moving or what is still. Every motion is relative, every perspective is valid. There is no centre to the universe, not in space and not in time. This principle shattered old notions. Before we imagined ourselves moving through a shared world. A world with one timeline, one agreed upon history. But special relativity revealed a new picture, a cosmos filled with overlapping realities, each one unfolding according to its own clock, each one correct in its own frame. The implications were enormous. Imagine two twins. One remains on Earth, the other boards a spacecraft and flies near the speed of light. When the traveller returns, she will have aged more slowly. Her clock will have counted fewer seconds. She is still young, her twin has grown older. Though they shared the same beginning, they did not share the same journey. This is the twin paradox. Not a paradox at all, but a direct consequence of time dilation. A story of symmetry, broken by motion, and it challenges our deepest intuitions about what it means to grow old, to remember, to live through time. What special relativity offers us is a mirror, one in which we glimpse the hidden geometry of reality. Space and time are no longer separate dimensions. They're joined, forming a four-dimensional fabric called space-time. And within this fabric, all paths are possible. Some curve gently, some twist and fold, but all are real. The dream that began in Bern did not end with a single theory. It led onward, to deeper mysteries, to the influence of gravity, to the warping of time, not just by speed but by mass. And soon Einstein would discover that even space-time could be pulled, curved and shaped by the presence of matter. But that part of the story comes next. For now, let us pause and rest in this moment, a world where light defines all things, where time is not absolute, and where your journey through the universe is your own unique path through the flowing tapestry of space-time. Close your eyes for a moment and imagine the impossible. You're no longer bound by muscle or machine. You have become a being of pure perception, riding on the edge of a single beam of light as it escapes a distant star. Ahead of you stretches the black canvas of space, still and vast. Around you, the stars shimmer like frozen echoes. There is no sound here, only motion. But even that begins to feel strange. As you accelerate toward the speed of light, something curious begins to happen. The universe ahead of you seems to flatten. Colours stretch toward red, then vanish. The stars, once scattered across the heavens, begin to bunch together at the front of your vision. Time, which once ticked steadily in your mind like a familiar drumbeat, now slows. Seconds stretch into minutes, minutes into hours, and still you race onward, feeling the weight of motion press against the world itself. From your perspective, you're simply moving faster. But to an observer watching you from a distance, something far more extraordinary is taking place. Your body seems to compress. Your time appears to drift. Your heartbeat slows. Your very sense of now begins to diverge from theirs. This is not an illusion. It is not an artifact of error or perception. It is a consequence of motion approaching the limit, the cosmic speed limit, the speed of light itself. And light, for all its velocity, remains untouchable. No matter how hard you try to chase it, no matter how fast you move, it always stays just ahead, forever beyond your grasp. It does not slow down. It does not speed up. Light is constant, and so the universe must bend around it. To preserve that constancy, time itself must change. And it does. It stretches. For the faster you move, the slower your own time flows. Your seconds become elongated. Your sense of now becomes narrower. If you could somehow return from this journey, you would find that the world you left behind has aged more than you have, that the people you loved have grown older, that the earth has turned many more times than you expected. This is the strange gift of motion, not just to travel through space, but through time itself. Time dilation is one of those ideas that feels like science fiction, until you see it written in the bones of reality. Physicists have watched it happen in the lab, not with dreams, but with particles. There are tiny, unstable particles called muons, born high in Earth's upper atmosphere by the collision of cosmic rays. These muons are short-lived. In the blink of an eye, they decay into other particles. On paper, they should vanish before they ever reach the ground. And yet, somehow, they do. Why? Because they are moving so fast, so close to the speed of light, that their internal clocks are running slow. From their own point of view, they exist only for a moment. But from ours, their lives have stretched. They live longer because they are racing through space, and space has made a trade. Time has yielded. A similar trade happens to astronauts aboard the International Space Station. Orbiting Earth at over 17,000 miles per hour, they experience time just a little more slowly than those on the surface. The effect is small, fractions of a second, but measurable. After 6 months in orbit, an astronaut returns to Earth, having aged ever so slightly less than their twin who remained behind. Even our technology must account for this. The satellites that power the global positioning system orbit far above us, moving fast and suspended in weaker gravity. If their clocks were not corrected for both their motion and their altitude, their signals would be off by miles. Every time your phone maps a route, it whispers a thank you to Einstein, adjusting for the dance between motion and time. It is humbling to realize that this is not a metaphor or an abstraction. It is woven into the very fabric of how the universe works. And yet, as strange as it may seem, there is something deeply human about it. For don't we all feel in certain moments that time speeds up or slows down? The heartbeat that races in fear, the long stillness of a quiet morning, the frozen moment of love or loss, when the world seems to stop moving. Perhaps in some way, our own inner clocks are already telling us that time is not as fixed as we once believed. That reality is not measured solely by the numbers on a dial, but by the shape of experience itself. There is something deeply poetic in the realization that time is not a straight and narrow corridor, but a bendable, stretchable terrain, one shaped by how we move and where we stand. And within this landscape, we are each the centre of our own unfolding present. This idea that each of us carries our own personal now is at once simple and staggering. It means that there is no universal present, no shared moment that binds the whole universe together. What feels like now to you may not be now to someone on a planet circling a distant star, or even to someone hurtling past you in a spacecraft at a fraction of light speed. Every conscious being, in every frame of reference, experiences its own private flow of time. And yet, from each of these isolated moments, the universe still holds together. Events remain consistent. Causality is preserved. If one thing causes another, the order remains true, even if the exact timing of the events shifts between observers. This is the silent agreement that keeps the cosmos coherent. Even when time itself is stretched thin, the threads do not break. And so we find ourselves asking, what is the true nature of the present? Is the present simply what we remember most vividly? Is it the thin edge of memory and anticipation? Or is it just the slice of the universe that our consciousness happens to be touching? Einstein himself once said that the distinction between past, present, and future is only a stubborn illusion. That time, in its totality, might be more like a landscape, one in which all moments exist at once. Some we can see, some we cannot, but all are there in the great fabric of space-time. Perhaps, then, our lives are not lines drawn through time, but curves that loop and spiral, each shaped by motion and memory. Perhaps every moment we live is already part of a larger whole, a whole we glimpse only in flashes, in dreams, or in the quiet moments between thoughts. And perhaps that is the true gift of relativity, not just to understand the mechanics of time, but to feel with quiet awe that we are always moving through a changing landscape, each breath a step, each thought a ripple, each memory a light glimmering on the path behind us. Time is not fixed, and neither are we. We are dancers in a shifting rhythm, travellers on a journey shaped not only by where we are, but by how we move, and our next step will take us into gravity's embrace. You may not feel it as you lie still beneath your covers, but right now, gravity is reaching up through the floor, quietly pulling you towards the centre of the earth. Not harshly, not urgently, but gently, like the soft tension of a stretched string holding you in place. We think of gravity as a downward force, something that tugs on our bodies, holds us to the planet, and makes objects fall when dropped. But this is only the surface understanding. The deeper truth is more elegant, more beautiful, and far more strange. Gravity, as Einstein revealed, is not a force in the traditional sense. It is the shape of space and time themselves. When you place a heavy object on a soft sheet, the fabric dips. Other objects, rolling nearby, are drawn towards that dip, not because they are pulled, but because the surface itself is curved. This is how gravity works in the universe. Mass bends the fabric of space-time, and where that fabric curves, other objects follow its contours. Even light, that stubborn traveller with no mass at all, follows the curves. When it passes near a massive object like a star or a black hole, its path bends, just as a marble would roll inward along a stretched sheet. But the bending of space-time has another consequence, one far more subtle than the movement of stars. It affects time itself. In a gravitational field, time runs more slowly. The deeper you are in the curve, the closer you are to the source of gravity, the slower your clock will tick compared to someone farther away. You could test this on Earth, place 2 atomic clocks on the same mountain, then carry one down to the base, let them tick away in silence. Over time, the clock at sea level will fall ever so slightly behind, not by minutes or hours, but by a sliver of a second. Yet this difference is real, measurable, inevitable. It is as if time thickens in the presence of gravity, as if the very rhythm of the universe slows in the company of mass. We walk through this distortion every day, unaware of how it shapes our experience. But in the places where gravity grows strong, near collapsed stars, near the mouths of black holes, the effect becomes undeniable. There time itself begins to stretch, and for an outside observer, it nearly stops. Imagine an astronaut hovering far above a massive planet. Her spacecraft glides in a high, steady orbit. She gazes down at the swirling clouds, the vast canyons, the golden glow of a distant sun. On the surface of that planet, her companion waits, standing beneath the weight of gravity, feeling its full pull. To each of them, time flows as it always has. Their watches tick normally, their thoughts move naturally. But if they could compare their clocks after some time apart, they would find a curious truth. The one who remained closer to the planet's surface aged more slowly. This is not science fiction, this is general relativity, a theory that revealed mass and gravity do not just shape where objects move, but how time moves through them. It is why clocks in satellites run slightly faster than clocks on the ground. It is why GPS systems need constant corrections. It is why astronauts who live aboard the International Space Station must account for not one, but 2 forms of time distortion: the time they gain from orbiting quickly, and the time they lose from being farther from Earth's mass. And it is why, in the most extreme corners of the cosmos, we encounter places where time becomes almost meaningless. Consider a neutron star, the collapsed core of a once massive sun, now crushed into a sphere no wider than a city. Its gravity is so intense, its density so great, that the surface of the star exists within a steep well of space-time curvature. Any clock placed on its surface would tick far more slowly than one in open space, and a traveller standing near it, if such a thing were possible, would see the universe beyond race ahead in fast forward, while their own thoughts crawled. But even the neutron star pales beside the black hole. Here the curve becomes a cliff. Time slows to a crawl as you approach it, and once you pass a certain invisible boundary, known as the event horizon, time, from the outside perspective, appears to stop completely, to the person falling in, nothing seems amiss. They drift inward, unknowing, unchanged. But to those watching from afar, their final moments stretch toward infinity, frozen forever at the edge. This is the paradox of gravity. It does not only hold you, it holds your time. It is a strange thought, that the stronger the gravity, the slower the time. But in a way it feels familiar. Heavy moments in life always seem to last longer. A second stretched by anxiety, a minute thick with grief. Time slows under weight, whether physical or emotional. Perhaps that is nature whispering truth in metaphor. But here, in the realm of physics, it is not metaphor, it is geometry. When Einstein unveiled his general theory of relativity in 1915, he gave us more than equations. He gave us a new intuition, that space-time is a kind of fabric, stretched by mass, shaped by motion, and that the passage of time is nothing more than the path you take through that fabric. If you climb a mountain, you move against gravity. Time ticks faster. If you descend into a valley, time ticks slower. But you never feel the difference because your body, your brain, your cells, your thoughts, they all slow together. You're inside the distortion. But if you could look outside, if you could compare yourself to someone far away, you would see the truth. You have slipped behind. The Earth, then, is not just a place. It is a clock tower carved from stone. Every object with mass is a clockmaker, warping time in its orbit. And as we look deeper into the universe, we begin to see these distortions everywhere. Galaxies clustered like raindrops in slow motion, light bent around invisible wells, ancient starlight stretched by the expansion of space, time revealed not as a line, but as a curved and trembling surface. This is the dream Einstein gave us, not just a theory of gravity, but a map to the hidden shapes of time. And now, having followed that map into the depths of mass and motion, we prepare to return to the twin paradox, no longer as a curious puzzle, but as a living truth. Because when you move fast enough, when you travel far enough, you do not just visit new places, you come back, changed. Imagine them side by side in childhood, two twins lying in a field beneath a violet dusk, staring up at the stars. Their lives are braided like strands of the same thread. Shared birthdays, mirrored laughter, identical DNA. They run the same race, breathe the same air, and dream the same dreams. As they grow older, their paths diverge in the way all lives eventually must, but their hearts remain synchronized. Two minds, one rhythm, until one day one of them leaves. Not in the way we often mean, not for college or for work, but truly leaves. She boards a spacecraft bound for the stars. A sleek vessel, engineered to approach the speed of light, humming with power and possibility. Her twin stands at the launch pad, hand raised in farewell. A moment shared, a final wave. To the traveller, the journey feels swift. The stars blur past her porthole as she accelerates. There is no drama, no sudden rupture of time. Her heart beats. Meals come and go. Sleep arrives and passes. She reads, writes, and dreams. The days unfold with their familiar rhythm. But on Earth, time holds a different story. As her ship departs the solar system and races into interstellar darkness, Earth continues to turn. Her sister lives through birthdays, through seasons, through the quiet erosion of decades. She watches friends age, cities change, forests grow old, and burn and grow again. She carries memories the traveller will never have, moments that fall through her fingers like sand, while the other twin floats far from the world they once called home. Eventually the traveller turns back. This moment, the turn, is critical. In the language of physics, it is where symmetry breaks. Up until now, both twins have experienced time in ways they believe to be equivalent. But the traveller must decelerate, pivot, and accelerate again to return home. That act of changing direction, of altering her frame of reference, is the key. It is not merely distance or motion that separates them. It is this shift, this bending of her world line, that will leave the deeper mark. And when she lands, what she finds is breathtaking. She steps from the ship, expecting a reunion. But standing before her is not the same twin she remembered. The face is older, creased by time's gentle insistence. The eyes are wise but weighed by memory. The traveller, unchanged in her youth, now looks upon someone who has lived a lifetime without her. And though their bond remains, something fundamental has shifted. Not their love, but their clocks. To truly grasp what has happened, we must step beyond metaphor and into the geometry of space-time itself. In the universe, Einstein revealed, time is not separate from space. They're one entity, a fabric called space-time, through which everything moves. Every object, every person, every beam of light traces a path through this four-dimensional fabric. These paths are known as world lines, and the shape of your world line determines how much time you personally experience. Imagine a giant diagram with space on one axis and time on the other. A person standing still traces a straight vertical line, motionless in space, but moving steadily through time. Someone walking traces a slightly tilted path. A spacecraft racing near the speed of light curves steeply through the diagram, tilting deeply into space. But here's the extraordinary part. The universe grants each of these paths the same total interval, a kind of cosmic budget. You can spend it all in time, or you can spend some in space. But the more you move through space, the less time is left for you. It's as if existence itself demands a trade. Fast motion borrows against your future. It shortens the number of seconds you're allowed to personally experience. This is the heart of time dilation. It isn't just that one twin saw the other aging faster, it's that their journeys through space-time were genuinely different. One moved primarily through time, staying almost stationary in space. The other curved through space at incredible velocity, and so experienced less time in exchange. When the traveller returns, their world lines reunite, but they are no longer equal. One is longer, one is shorter. The distance between them is not just measured in miles, but in seconds, minutes, years. And all of this is predicted with astonishing precision. This isn't philosophy. It isn't poetry pretending to be science. Physicists have tested these predictions again and again. Muons created in Earth's atmosphere reach the ground because they are moving so fast that their internal clocks slow down. GPS satellites constantly correct for time dilation to keep your maps from drifting. Particle accelerators routinely observe particles with extended lifespans simply because they are racing through space. The twin paradox is not just a parable, it is the lived reality of high-speed physics. And yet, for all its elegance, it still leaves us with something deeper to reflect on. Because when time flows differently for two people who once shared everything, what does that mean for memory, for connection, for the soul? Beyond the math, beyond the diagrams, there is a very human mystery at the centre of this story. What does it feel like to come home and find your twin has lived a lifetime without you? The traveller may not have sensed time's distortion. She lived her journey as anyone would live a life, moment by moment, unaware that anything was unusual. But upon returning, she is faced with a truth that no equation can soften. She has missed a portion of someone else's life. And her sister, the one who waited, has lived through decades of absence, while for the traveller, only months may have passed. There is no malice in this, no betrayal, only the quiet reality that time is not something we all share equally, that even our deepest connections are shaped, at the root, by how we move through the universe, and this touches something ancient in us. Haven't we all felt the strange elasticity of time? The years that fly by when we're distracted, the hours that stretch during grief, the dissonance between your own timeline and someone else's. A friend calls after years apart and says, "It feels like no time has passed," but it has, for both of you, just in different directions. The twin paradox reminds us that aging is not an absolute, that the arrow of time is not the same for everyone, and perhaps most beautifully, that motion leaves marks not just in the dust we kick up behind us, but in the very seconds we are given to breathe. When we part from the people we love, we are always taking different paths through space-time. even if we don't board spaceships. When we return, we carry with us the weight of the journey, not always visible in our skin, but written deep in our bones. And yet, even with those differences, we still find each other. The paradox is not in the physics, it's in the feeling. The universe allows both twins to be right. Both clocks are accurate. Both experiences are true. That's the magic. Reality is not singular, it is plural. And time, as Einstein taught us, is not a ruler etched in stone. It is a river with many channels, each one carrying a life downstream at its own speed. And so the paradox becomes a poem, a story not only about how time moves, but about how we move through time, together, apart, and sometimes forever changed. Look up, though you may not see them, they're there. Orbiting quietly above your head are dozens of small, fast-moving sentinels, each no larger than a compact car, flying silently through the sky. These are the satellites that make up the Global Positioning System, GPS, and they are among the most practical time machines ever built. It might seem strange to describe a navigation network as a time machine, but at its core, GPS is not really about location. It is about time. Every GPS satellite carries within it an extraordinarily precise atomic clock. These clocks don't tell time like your wristwatch. They measure the vibrations of atoms, usually cesium or rubidium, as they oscillate at exact, predictable frequencies. These oscillations are so regular that they can measure time to within billionths of a second. Why is such precision necessary? Because when you open a map on your phone, it determines your position based on how long it takes for signals to reach you from multiple satellites. The difference in arrival times, just a few nanoseconds, can mean the difference between placing you in your driveway or halfway down the street. In an ideal universe, that would be the end of the story. But in ours, time bends. The satellites, orbiting at about 12,500 miles above Earth's surface and travelling at roughly 8,700 miles per hour, experience both forms of time dilation simultaneously. First, because they are moving quickly, special relativity tells us their clocks should tick more slowly compared to those on the ground. But second, because they are farther from Earth's gravitational field, general relativity tells us their clocks should tick faster than those closer to the planet. And here is the remarkable part. These two effects don't cancel out. They add up in opposite directions. Special relativity causes the satellite's time to slow down by about 7 microseconds per day. General relativity, due to the weaker gravity at orbital altitude, speeds their time up by about 45 microseconds per day. The net effect? Their clocks tick faster than those on Earth by about 38 microseconds every single day. That might not sound like much, but without correcting for this discrepancy, GPS systems would accumulate an error of about 6 miles per day. In just a matter of weeks, your location would be hopelessly lost. So what do? We program the satellites to account for time dilation. We tell the onboard clocks to tick slightly slower than Earth-based clocks from the start, so that by the time they're launched and operational, their relativistically adjusted timing aligns with ours. And in doing so, we build a bridge, a technological harmony between the warped geometry of space and the practical needs of human life. Without relativity, the GPS system would collapse under its own errors. But thanks to Einstein's insights, we can navigate not just through cities, but through space-time itself. Every time you get directions, you are relying on the fact that time is not absolute. Beneath the Earth's surface, in a ring of tunnels stretching 17 miles beneath the French-Swiss border, another kind of machine bends time, not to find directions, but to crack the code of the universe. This is the Large Hadron Collider, or LHC, operated by CERN. It is the most powerful particle accelerator ever built by humankind, and it exists for a singular purpose: to fling particles at incredible speeds, smash them together, and examine the fragments to understand what reality is made of. Here in this subterranean cathedral of precision, time becomes malleable in ways that defy everyday intuition. Inside the LHC, Protons are injected into a vacuum-sealed ring and accelerated to 99.999991%, the speed of light. At this velocity, the protons complete over 11,000 revolutions every second. They move so fast that their internal experience of time slows dramatically. If you could somehow ride along with one of them, you would find that while the outside world sees milliseconds fly past, your own internal clock would tick in a dreamy, slowed-down rhythm. This is not a metaphor. The effects of time dilation at these speeds are so extreme that certain unstable particles that should decay in less than a millionth of a second, are observed to persist much longer. Consider the muon again. Muons are elementary particles similar to electrons, but with greater mass. At rest, they decay in about 2.2 microseconds. But when accelerated to near-light speeds in a collider, they live hundreds of times longer. Their time, relative to the laboratory frame, has been stretched. They exist in a kind of suspended animation. And this is crucial for physics, because many of the particles that define the standard model of particle physics, such as bottom quarks or tau leptons, are fleeting, ghost-like entities. To study them, we must slow down their decay, not with force but with speed. By hurling them close to light speed, we allow time dilation to stretch their existence. This gives detectors more time to capture their signatures, more time to measure their spin, charge and behaviour. Without this relativistic extension of lifespan, most subatomic particles would vanish before we could ever see them. But the LHC does more than harness time dilation. It reveals something deeper, that the structure of reality, the rules that govern mass, charge and interaction, are not just present in stillness, but emerge most clearly when we press the boundaries of motion. In stillness, the universe whispers. In motion, it reveals. And so we build machines that fling particles faster and faster, not just to split atoms, but to bend time itself, so that for just a fraction of a second, we might glimpse the hidden architecture of matter. Let us now shift from satellites and colliders to the horizon of what may come, where time dilation becomes not just a correction, but a destination. In the near future, as humans begin to contemplate voyages beyond the moon, toward Mars and perhaps beyond, we enter a realm where relativistic effects, while still small, will begin to matter. A spacecraft travelling to Mars at conventional speeds would not experience significant time dilation. But the dream persists. What if we could build a vessel capable of reaching a substantial fraction of the speed of light? In such a ship, time would begin to warp for the crew aboard. Consider a journey to the nearest star system, Alpha Centauri, which lies about 4.3 light-years away. At 1/10 the speed of light. The trip would take over 40 years from Earth's perspective, and nearly the same for those aboard the ship, but increase the speed to 90% of light, and something magical happens. To observers on Earth, the journey still takes just under 5 years. But to those on board, due to time dilation, the voyage might feel like only 2 years. At 99% of light speed, the trip would still appear to take 4 years from Earth's frame, but the passengers would feel only 7 months pass. This is the dream of relativistic travel, not faster than light propulsion, but the bending of time itself. For the traveller, distances collapse, time condenses, the stars grow closer, not because space shrinks, but because their own timeline tightens. And while we are not yet building ships of that speed, the principle already shapes the way we imagine interstellar engineering. Relativistic spacecraft must account not only for propulsion and shielding, but for clocks, navigation systems, and communication delays that shift as time bends. If a probe was sent at near light speed toward another star, the designers must calculate not just the physics of acceleration and fuel, but how long the onboard systems will think the journey takes, and how to synchronize that timeline with mission control on Earth. Even now, in experimental labs, physicists are exploring atomic clocks so precise they can measure time dilation from a shift of just 1 centimeter in altitude. These clocks can detect the difference in time between your head and your feet. They are the precursors to a future in which time becomes an engineering parameter, a quantity that must be stabilized, controlled, and measured like voltage or temperature. The deeper message is this: relativity is not a footnote, it is not a quirk, it is the operating system of the universe. And we at last are beginning to write code in its language. We have stepped beyond philosophy, beyond metaphor, and into a world where the shape of your motion changes the structure of your time, where machines bend time with precision, and where every moment is measured not by how long it lasts, but by how fast it flies. In all the known cosmos, there is no greater warper of time than a black hole. These strange objects, predicted by general relativity and now confirmed by observation, are regions of space where gravity has become so powerful that even light cannot escape. They are the end point of collapse, the final punctuation mark in the life of a massive star. But they are more than that. They are laboratories of the impossible, places where time, as we understand it, begins to break down. To comprehend what a black hole does to time, we must understand what it means for space to bend. As we've explored, mass curves space-time, and the greater the mass, the deeper the curve. But a black hole is not just massive, it is compact. It concentrates matter into an infinitely small volume known as a singularity. All the mass of a collapsed star crushed into a single point. Around this singularity lies the event horizon, a boundary beyond which no information, no signal, no light, no possibility of return exists. From a distance, a black hole might look serene, a dark circle in the fabric of the sky, surrounded by a halo of glowing matter spiraling inward. But approach it, and reality begins to shift. The gravitational field grows stronger, the warping of space-time becomes more pronounced, and time itself, always flowing, always steady, begins to stretch thin. Now imagine a spacecraft descending toward that event horizon. From the perspective of an outside observer, watching through a telescope, the ship begins to slow as it nears the black hole. Its motion becomes sluggish. Its clock ticks ever more slowly. The radio signals it emits arrive later and later, redshifted to lower frequencies. The crew appears frozen in time, suspended just above the threshold, never quite crossing. But from the perspective of the crew, everything seems normal. They do not feel time slowing. Their hearts beat steadily. Their instruments hum. They cross the horizon without fanfare, without resistance. But once inside, their fate is sealed. The curvature of space-time has become so steep that all paths lead inward. There is no up or away anymore. Only inward, only forward, only towards the singularity. This disparity between observers, those outside and those falling in, is not a bug in physics. It is a feature. It is how relativity protects causality, how the universe preserves the consistency of events. But it also means something extraordinary. To fall into a black hole is to enter a place where your time slows to near zero, relative to the universe outside. Millions or billions of years could pass in the cosmos beyond, while you experience only minutes. If the black hole survives long enough, and if someone could observe your descent from afar, you would appear as a frozen echo, forever falling, never arriving. And in that echo, time itself becomes a mirror, a reflection distorted by gravity, a slow-motion replay of a moment the universe never quite finishes watching. Though black holes receive the most attention in discussions of extreme time dilation, they are not the only cosmic structures capable of reshaping the tempo of existence. Neutron stars, too, are sculptors of time, dense, collapsed remnants of massive stars that did not quite reach the black hole threshold. A neutron star is a paradox wrapped in physics. Imagine compressing the mass of the sun into a sphere no larger than a city. What remains is a gravitational field of breathtaking intensity, enough to collapse atoms themselves, to press electrons into protons, and leave behind a fluid sea of neutrons. The surface gravity of a neutron star is roughly 200 billion times stronger than Earth's. A pebble dropped onto it would hit the ground at close to the speed of light, And in such gravity, time bends again. The closer you stand to a neutron star, the slower your clock ticks relative to someone far away. Atomic transitions slow down, heartbeats stretch, decay processes extend. But here, unlike black holes, the boundary is not hidden behind an event's horizon. The neutron star still has a surface, solid, visible, and unimaginably violent. Some neutron stars spin rapidly, emitting twin beams of radiation from their magnetic poles. These are pulsars, cosmic lighthouses sweeping the sky with uncanny precision. In fact, pulsars are among the most reliable timekeepers in the universe. So reliable, they have been proposed as a basis for interstellar navigation. But even their timekeeping must bow to gravity. The pulses we detect from neutron stars are already stretched by the gravity they must escape. The signal that reaches us is slightly redshifted, its frequency lowered, its time signature bent. And if we could stand on the surface of a neutron star and send a message outward, the people who received it would hear our voice slowed, drawn out like a record played too slowly. These are not fantasy speculations. These are observations backed by pulsar timing arrays, by binary systems where neutron stars orbit other stars, and by gravitational wave detections that confirm the predictions of general relativity to astonishing precision. And they tell us something sobering. Time, for all its familiarity, is fragile. It is susceptible. It can be stretched and pulled and bent, not just by motion, but by matter. And in the presence of enough matter, even the seconds themselves can be diluted. A second may be a second in your own mind, but elsewhere in the universe, under different skies, it is something else entirely. What happens when we go beyond the known? Not just to black holes or neutron stars, but to theoretical structures, places we have not yet seen but which mathematics allows to exist. Among these are wormholes, tunnels through space-time that connect distant points. They emerge naturally in the equations of general relativity, and though no one has observed one, their potential implications for time are staggering. A stable wormhole, if it could exist, would act like a shortcut through the fabric of the cosmos, not just through space, but through time. If one end of a wormhole experiences strong gravitational time dilation, say by sitting near a massive body, while the other remains in a weaker field, the two ends fall out of temporal sync. One becomes older, one remains younger. A traveller who enters the wormhole could, in theory, emerge in the past or the future relative to the outside universe. This is not science fiction. This is a direct consequence of time dilation and the bending of space-time under gravity. Of course, stable wormholes would require exotic matter, substances with negative energy density, not yet discovered in nature. But quantum field theory, in certain vacuum states, allows for fluctuations that behave this way. Casimir effects, vacuum energies, quantum anomalies. What matters more than whether they exist today is that our current theories say they could. And where wormholes suggest travel through time, other speculative entities suggest the same. Cosmic strings, infinitely thin, unimaginably dense defects in space-time left over from the early universe, could also bend time, allowing for closed time-like curves. That is, loops in time, paths that return to their own past. These are not mainstream predictions, and they come with paradoxes that have no resolution. But even their possibility suggests something profound, that time as it exists in our local world may be a local phenomenon, a condition of our region of space-time, that elsewhere, under different curvatures, pressures and energies, the rules may not apply the same way. And so we look upward, not just to stars, but to the geometry that holds them. We listen to the pulses of distant pulsars, the whispers of gravitational waves, the afterglow of the Big Bang itself, and we realize the story of time is not finished. We are still writing it, still discovering the places where it bends and folds and sings. And as we listen to the echoes at the edge of forever, we find that the great silence of space is not empty after all. It is filled with clocks ticking at different speeds, with seconds stretched like starlight, and with the promise that the future may be stranger than time itself. We began with seconds, measured ticks on a clock, the swing of a pendulum, the pulse of a heart. We spoke of time as if it were a thing, steady, tangible, moving forward like the turning hands of a dial. But now, after our journey through the universe, through light and gravity, through clocks that run slow and particles that stretch their lives, we must ask again, what is time? Not how it behaves, but what it truly is. For physics, time is a coordinate, a label assigned to events so we can place them in order. It's part of the scaffolding we use to describe motion and change. But that scaffolding may not be fundamental. It may not be stitched into the fabric of reality the way we assume. Many of the most successful equations in physics, the laws of quantum mechanics, the structure of Einstein's field equations, the principles of electromagnetism, do not require time to flow in one direction. They work just as well if you reverse the sequence. The past and future are symmetrical in the math. What matters are relationships, how one thing changes in comparison to another. So why then do we remember the past and not the future? Why does cream mix into coffee but never unmix? Why do we age and never grow younger? The answer lies not in the laws themselves, but in a boundary condition, a rule whispered at the beginning of time. The arrow of time, as we experience it, is believed to be born from entropy, the gradual increase of disorder in the universe. This is the second law of thermodynamics. It tells us that systems tend toward greater randomness, and with it time seems to march forward. But entropy, too, is not a force. It is a perspective, a way of counting what we can't see. As the universe spreads and cools and structures dissolve, our memories fade, our certainty erodes, and so we feel time slipping away, even if the fundamental laws remain untouched by its direction. Perhaps the reason we feel time's arrow is because we are built to survive in its shadow. Our brains evolved to model cause and effect. Our memories form in one direction. And so, to us, time appears to flow forward. But maybe it is we who are flowing, sliding across a surface whose shape we do not fully understand. Time may not be a river. It may be a map. And you are not drifting forward. You're walking across it. Let us now walk forward, far forward, beyond human civilization, beyond Earth, beyond even the stars themselves. Imagine a time when the universe has aged beyond recognition. The galaxies have drifted too far to see one another. The stars have all burned their fuel. Only cold embers remain, slowly fading. Black holes evaporate over trillions of years, their mass lost to quantum radiation. The last light dims, the last warmth bleeds out. The cosmos becomes dark, thin, and silent. This is the heat death of the universe, a theoretical final state where entropy has reached its maximum, and all usable energy has been dispersed. In such a universe, time still exists, the equations still work, but with no change, no structure, no events, time loses its meaning. It becomes indistinguishable from stillness. This is not a prophecy, it is a boundary condition, an extrapolation of the laws we know. But even in this far future, time is not gone. It is simply idle, sleeping, waiting, because time, like music, needs change, and in the absence of rhythm, the song goes quiet. What then becomes of memory? If time is a measure of change, then memory is its echo, the mind's way of recording the path it has taken. But if no changes remain, if entropy reaches its peak, then there are no more paths to walk. The mind fades, and with it the last witness to time. But some physicists speculate that the story might not end there. In the quietest corners of quantum theory, there are models where time emerges from entanglement, where time is not fundamental, but arises from the interweaving of relationships. If that's true, then time could be born again. A new configuration, a new observer, a new arrow. And the story starts over. Or maybe time is eternal. Not a river with a source and mouth, but a circle with no beginning and no end. Maybe this moment has happened before. Maybe you have heard these words in another life. Maybe beyond all entropy, time simply turns back upon itself and dreams again. And now, Voyager, you're here, at the edge of what can be said, the place where thought becomes feeling and measurement gives way to stillness. You have travelled with us through space-time, from the ticking of clocks to the slowing of hearts, from the satellites in orbit to the stars collapsing inward. You've followed beams of light, watched particles stretch their lives, and stood at the rim of black holes where time halts altogether. You've wandered among giants that bend the hours, touched machines that measure the imperceptible, and drifted through moments where the universe forgot how to change. But here, there is nothing left to explain, only the quiet, only the slow breathing of space itself, because time at its deepest is not something we count, but something we carry. It is the distance between memory and anticipation, the gap between what was and what may be. And sometimes in rare moments like this, it narrows to nothing. Right now, there is no past, no future, only this moment, this still point in the turning world, this breath, this heartbeat. Let go of the ticking, let go of the counting, let go of the need to know where you are in the story. Because here, in the silence between the seconds, time sleeps, and so may you. Good night, Voyager. Rest well.